then let's invite Dr. Han Hu. So Han Hu is currently a principal researcher in Microsoft Research Asia and an adjunct PhD advisor at Xi'an Jiaotong University. His main research interests include visual architecture design, self-supervised representation learning, and visual language representation learning. His paper, Swin Transformer, won the CVPR-2022 Best Paper Award and is now widely used in academia and industry. He received his PhD and bachelor's degree from Tsinghua University in 2014 and 2008, respectively. His PhD dissertation received the Excellent Doctoral Dissertation Award of Chinese Association of Artificial Intelligence. He visited the University of Pennsylvania for half a year in 2012 and worked in Institute of Deep Learning, Baidu Research, between 2014 and 2016. He served as an area chair for CVPR 2021 and 2022. So, are you there?
Yes.
Dr. Han Hu. Okay, yeah, I'll stop share.
Can you see my screen?
Yes.
Okay, thank you, Wen. Hi, everyone. I'm Han Hu from Microsoft Research Asia. The title of this talk is Convergence of Architectures and Learning Methods in Computer Vision with Other AI Fields. The goal of AI is to make computers as intelligent as the human brains or even beyond. So let's first look at the human brain. This is a illustration of the human brain, and this wrinkled part is called the neocortex. It's responsible for most of our human intelligence, including visual, auditory, language, motor, gustatory, consciousness, and so on. Although it has many different functional areas, they are very uniform in structure. By unfolding the neocortex, its shape and size are like a dinner tissue, about 40 centimeters long and 50 centimeters wide and 2.5 millimeters thick. Its vertical neural structure is almost identical. Almost all places have 6 layers according to 3 types of staining methods. That is, all these very different abilities, as we mentioned earlier, are implemented using a single neural structure. In fact, this is right a key to the success of human beings, that human beings can quickly adapt to new capabilities and environments. Here is an interesting finding published 20 years ago in a Nature magazine. Please see the left figure. This is a mouse brain. The blue arrows are the neuron paths of how the visual signals are processed. The red arrow are the neuron paths of how the audio signals are processed. The scientists revealed the neuron path as the red figure, such that both the auditory and the visual cortices received the visual signals. After training, the scientists found that auditory cortex can also process visual signals. This experiment indicates that the same cortices can be used for different human abilities. Neural architecture is innate. It requires nurture to work out different capabilities, which correspond to what learning acts in artificial intelligence. Now, the learning methods are also believed to be universal. I studied by Inner-Cohen's famous cake analogy. So in this analogy, different learning methods are mapped to parts of a cake. For example, he thought reinforcement learning is like the cherry. It's very shiny, but the learning signal is too sparse. Then supervised learning is like the icing, which is sweet, but it contains no bit information. So he bet on self learning. He thought self learning is like cake genoise, which should be the most fundamental learning paradigm to drive the learning of a network. In fact, what inspired the inner current is the learning mechanism of a baby. Our baby learns to perceive the world through observation by either the sight, the hearing, the touch, and so on. Observations contain rich data, and through some self-supervised learning tasks and this rich data, our brains are learning all the time and helps the brain to possess strong perception abilities. The recent study in brain science has suggested that predictive learning may be one of the most fundamental steps of learning tasks for human beings to build their perception abilities. Predictive learning trains the network through comparing the difference between prediction and the actual pictures that appear later. In fact, we live in a world of space and time. Our brains are always predicting what the next moment is. For example, predicting what the picture of a different viewpoint is after our eye movement. Here shows an illustration. The pink part represents the past, and then the light blue indicates the future. And we can learn our visual system by predicting the light green part. A further question is how exactly predictive learning is conducted inside a brain. Now, it's believed that the thalamus plays a key role. Please see this figure. It shows an example of visual perception. So starting from the retina, the transmission of nerves will first reach thalamus, and then it will further reach the cortex. And it makes predictions when going back to thalamus. So in this way, they can drive learning by the difference between the prediction and the real picture of the next moment. And beyond the vision, other senses also share similar learning mechanism, including hearing and touching. After talking about human brains, let's turn to artificial intelligence, particularly the computer vision field. We first talk about AI architectures. The past 2 years of computer vision was so exciting that we were ongoing architectural convergence in computer vision with natural language processing. 2 years ago, the mainstream architectures in different AI fields were largely different. In computer vision, convolutional neural network had been the dominant architecture for 30 years. In NLP, Transformer has been the dominant architecture since 2017. In social computing, the mainstream architecture was graph network. Now, let's review the evolution of mainstream architectures in 2 major AI fields, natural language processing and computer vision. Firstly, language and sequential data such as speech recognition. The most popular early architecture was LSTM. It's complex in design, using 4 gates to elaborate gradient explosions and the inability to transmit information over long distances. Until 2013, the revolutionary accuracy improvement in speech recognition is still built by LSTM. In 2014, Google's GRU model simplified the design of LSTM to have only 1 gate, while being similarly accurate in the machine translation problem. The next big architecture upgrade was in 2015, where RNN and attention are combined together to implement machine translation. RNN is used to encode a single language, and attention is used to model relationship between 2 languages. Then we all know that Transformer appeared in 2017, and it then becomes mainstream. Then let's look at the field of computer vision. Unlike NLP, we have been always using networks that are built by convolution layers. Convolution was first proposed in 1980s. Applied the convolution networks to a handwritten digital recognition problem when he worked at Bell Labs. It was one of the earliest practical systems in computer vision. In the age of deep learning, the AlexNet, GoogleNet, VGGNet, ResNet, and DanceNet, they are all built on convolution layers. It's natural to ask whether NLP and CV can use the same architecture. One way is to apply the mainstream architectures in computer vision to the field of natural language processing. We have known the current dominant architecture in NLP is Transformer, which was proposed in 2017. Almost at the same time, in May 2017, there was a work from Facebook to use convolution to solve the same machine translation problem. The network is named convolutional sequence-to-sequence. The performance was also very impressive, and it achieved results in machine translation at night time. And it also changed the machine translation model from sequential to parallel in training. 1 month later, so we know a transformer appeared on archive, and which achieved higher accuracy, and it was also built by a more elegant building component attention. Then everybody's attention was on transformers. And however, there are also some works continuously exploring convolution in NLP. For example, dynamic convolution in early 2019, and deformal convolution from our team. But unfortunately, they didn't become mainstream because transformers are so is continuously improved, and it can be combined well with BERT or GPT. So for now, transformer is still the dominant architecture in NLP. The other way is to adapt the mainstream architecture in NLP to computer vision. After several years continuous exploration, this road gained great attention, represented by 2 works. One is VIT from Google, and the other is Swin Transformer. Swin Transformer for the first time surpassed all previous CM methods by a large margin on 2 visual benchmarks. One is local detection, which is a region-level task that predicts location and categories of objects. Here are the best methods across years and COCO. Before Swin Transformer, all methods are based on a same backbone. Now, Transformer backbone has taken over on its benchmark, starting from Swin Transformer. Here is another benchmark called ADE 20K segmentation, which is a pixel-level task by labeling the category of every pixel. Also, in previous years, all methods are based on same backbone. Now, our transformer architecture becomes better. In particular, Swin Transformer surpassed the previous best method by 3.3. Since then, transformers took over more and more benchmarks in computer vision. Also note that although it was until 1 year ago that transformers started to take over CNN on various computer vision problems, the journey that applied attention layers for computer vision problems began soon after transformer was proposed in NLP. In November 2017, there were 2 popular works that apply attention layers to vision problems, including non-local neural network and the relation networks. The former use the self-attention modules to encode global dependency between pixels, while the latter builds relationship between objects, which result in the first end-to-end object detector. In April 2019, we developed local relation networks, which was the first full attention visual backbone. In fact, we have long believed that self-attention or transformers can act a universal architecture for different AI domains. Our belief comes from 2 reasons. Firstly, transformers can be treated as a general graph, where all concepts and their relationship can be modeled by a graph. The concepts can be either concrete or abstract. This general modeling capability is also partly attributed to the verification principle in building relationships between graph nodes. Please see the right illustration. No matter how different the input is, for example, the image patches in different scales, or the multi-model input such as text and image patches, their relationship can be all modeled by verification in an embedding space. This general capability enables transformers to model all kinds of relationships in computer vision, such as pixel-to-pixel, object-to-pixel, and object-to-object relationship, which almost cover all vision applications. During the last 5 years, our team has conducted a lot of research regarding these three kinds of visual relationship. I will briefly introduce 4 of them, highlighted in red. The first work was relation networks for object detection, which was published on CVPR-2018. This work aims to model the relationship between objects. Please see this image patch. It's rather different. It's not easy to figure out what it is by seeing this patch alone. However, if you stay in the context, it's easy to recognize the patch as a baseball glove after noting that a baseball player is holding it. This module helps to create the first fully end-to-end object detector. This depth attention module can be inserted into 2 steps of the fast assaying detector. Please see the red blocks in this pipeline. Firstly, it's inserted in the instance recognition head. Now, given this module, the objects can be jointly recognized instead of processed separately as in previous methods. The second is to do duplicate removal. In previous methods, duplicate removal is usually achieved by a handcrafted non-maximum separation method. By the self-attention module, we can make this step end-to-end learnable. So we came up with the first fully end-to-end object detector. Now end-to-end detection has been a common practice due to a follow-up famous paper named DTR, published on ECV 2020. One key of this paper to achieve end-to-end detection is also the attention module. The second work I would like to briefly introduce is local relation networks, published in ECV 2019. Its motivation is from a criticism of the convolution layer. In fact, the convolution layer is criticized to have low efficiency. Convolution performs a template matching using a fixed filters across all image positions. So please see this image. There are 3 boards with slightly different head poses. With the convolution layer, we need 3 channels to encode these 3 board heads, which is inefficient. Other than using fixed filters across image positions, transformer layer can use adaptive filters across positions. And in this way, potentially, we need only 1 channel to model different board head poses. By self-attention layers, we developed the first fully attention visual backbone. It's achieved by replacing all convolution layers in the ResNet with transformer layers, maintaining the same computation complexity. The network is named Local Relation Networks, LRNet for short. This curve shows comparison of this network with ResNet and IMNet 1000 calculation. The blue curve shows the result of ResNet with increasing kernel size, which is based on convolution layers. The orange curve shows the result of our local relation networks. The transformer-based local relation network is 2.7% better than ResNet. However, this network is not practical at night time due to slow inference speed. I will introduce Swin later, which address this problem. Another well-known work was Vanilla vision transformer, which directly applies the standard transformer used in NLP to the problem of computer vision. Please see this illustration on the right. The Vanilla vision transformer partitions an image into small patches and directly applies a transformer on these patches to output a class label. So it's very straightforward, and also it has demonstrated very good accuracy on image classification. We argue that this vanilla vision transformer doesn't consider the key difference between visual and text signals. First, a visual object can be in different scales, which advocates a hierarchical structure in architecture design. A fluffy cat is a fluffy cat, no matter how large it is. But for a sentence, the words or tokens have no scale variation. We cannot say, I am a fluffy cat. This is invalid in grammar. Second, the visual signals are usually smooth in space. For example, these two grass patches have similar texture, and they are both colored green. This property encourages no locality prior. In contrast, there is no spatial smoothness in a sentence. Thirdly, a visual object can be in different locations, which advocates translation invariance in architecture design. A fluffy cat is a fluffy cat, no matter where it is in an image. In contrast, a word is sensitive to its location. It has different part of speech when appearing at different locations. By using these computer vision priors, we can build a bridge from the standard transformer architecture in NLP to that in computer vision. This is an illustration of the standard transformer architecture in NLP. We can say it's plain with a similar solution at different layers. It computes the relationship among all words globally at each layer. It also accounts for absolute positions of each word in computation. So to build a bridge to computer vision, we introduce priors of hierarchy, locality, and translation invariance into the transformer architecture. And as a result, we came up with Swin Transformer, which performs strong on various vision problems. An important technical innovation of Swin Transformer is a shifted window approach. This design ensures our fast speed in real computation, particularly when compared to the traditional standing window approach used in our previous work of local regional words. So in the previous standing window approach, information was collected between neighboring pixels. That is, each pixel is centered on itself and takes a neighborhood window for calculation. To improve speed out, we propose a design that doesn't overlap the windows. You can say the non-overlapping windows in layer L. And to exchange information across different windows, we propose in layer L+1, we shift the window configuration by half a window so that the information in the previous layer can be exchanged between different windows. So what is next? Given that the basic modeling of computer vision is shifting from CNN to transformers, we believe that this is just a start, and then there is a long road in the front. So one important question to answer is whether vision models can benefit from scale up like that in NLP, because this is the most successful findings in NLP during the last 3 years. To answer this question, we trained a 3 billion parameter dense vision model, which is the world's largest and most effective vision model. Unlike previous billion scale vision models, which were only applied to the image classification problems, our model can be applied to broader visual tasks, such as object detection and spatial segmentation, which requires much higher resolution. It also reduces the requirements on very large label data sets, such as GPT 3 billion. GPT 3 billion has 3 billion images, and we only rely on 70 million images. The new model is named Swin-2G, and it set new records on four vision benchmarks, including IMNet 1000 V2, COCO detection, ADE 20K segmentation, and kinetics 400 action regulation. Also note that although Swin-2 has made one step forward, the visual models are still far smaller than that of NLP models. We can look at these curves. The gray curve represents the change in the size of NLP models, and the green curve represents the change in the size of visual models. We can say the gap is about 200 times, and the gap with the human brain is even larger. It's about 50,000 times. So the vision models still have a long way to go. As has been shown effective in both fields of natural language processing and computer vision, we expect transformer could be generic to arbitrary signals or domains, including social computing and AI for science. So Swin Transformer actually shows an example of how to apply transformers in a specific domain. Concretely, it can be recognized as a combination of generic transformer and several domain-specific pairs. The domain-specific pairs can be encoded by the existence of edges in a graph. This formula of generic transformer unit combining domain-specific pairs can be also set as a principle to guide architecture design in social computing or AI for science. For example, by this principle, graph former won a competition which predicts the quantum property of molecular graphs. After talking about architectures, now we turn to learning methods. For learning, we are mainly concerned about the pre-training, which is now a common practice as a first step for model training. Like architectures, the pre-training methods of different AI fields had been also different for a long time. For computer vision, supervised learning on IMNet 1000 had been a standard approach for a long time, whose goal is to classify the images into 1000 classes. For natural language processing, please see the figure on the right, the mainstream method is language modeling, such as BERT-based method, which is based on masked language modeling. And let's look at a more detailed block diagram of BERT. On the left is the pre-training step, where parts of the sentence are masked in the input section. And the goal of the network is to predict the token ID of those masked parts. Once it is pre-trained, it can be fine-tuned for a wide range of NLP tasks. We have known BERT is a milestone, and since BERT, almost all NLP tasks have been using transformer architecture and BERT or GPT-like pre-training methods. At the same time, in computer vision, although supervised pre-training approach has been the mainstream for a long time, there have been also many works exploring self-supervised pre-training. In fact, the pioneer work of autoencoder is a self-supervised approach. It has largely triggered the emergence of deep learning in computer vision. Here is a summary slide about self-supervised learning by Zisman a few years ago. Please look at the approach in a circle. It has been very close to the masked language modeling approach used in BERT. Yeah, this task is called imprinting. After many years continuous exploration, in 2020, there was a renaissance of self-supervised learning in computer vision, represented by MOCO, which is based on contrastive learning. And it, for the first time, surpassed the supervised approaches on 7 downstream tasks. Our team has also proposed an approach based on contrastive learning named KISS-Pro, and it's inspired by eye movements. The human we know the human eyes can usually move 3 to 4 times in 1 second. In fact, the picture presented on the retina changes greatly when the eye moves. But why don't we feel dizzy? This is because our brain is continuously predicting the picture after eye movement, so that when the new picture enters the retina, we will feel smooth. This is right the main idea behind the PIX Pro. So for image, we train the networks to have to make the features at the intersection of 2 cropped image views to be close to each other. The PIX Pro approach is not built by prediction, but by comparison. Recently, there is a big trend in the field of computer vision that to use GPT-like or BERT-like method for self-serve pre-training. And many methods have been proposed, including ImageGPT, BERT, CMM, MAE, PICO, data to actor, and CAE method. Please look at the right, which shows CMM from our group and MAE from Meta. The methods are very simple. So for each image, we mask a large portion of image patches and train the vision network to predict these missing values. And so the model is pre-trained. These approaches are called mask image modeling. Regarding its strong connection to mask language modeling like BERT, it deserves carefully examining the difference of vision and language signals so as to make it work well for computer vision. So let's first look at the NLP and the training task and left, where we will mask the word fluffy. The goal of learning is to recover this word. We also notice that the text has no spatial smoothness and the text tokens are semantically high level and discrete. In contrast, please see the right. The image is highly coordinated in space and the signal is raw, continuous, and low level. Regarding these differences, we choose to use a much larger portion of masking area, for example, 60%, instead of a small ratio of 15%. This adjustment to use a large portion of masking area and a large patch size, for example, 32, was a key to the effectiveness of CMM. In the end, there is a single message to take home, that computer vision in the past 2 years have experienced architectural and learning convergence with natural language processing and other AI fields. In architectures, transformers have been the mainstream architectures for both NLP and CV. In learning, predicting unknown input has been important pre-text task for both NLP and CV. So it has been a year to embrace converged architectures and learning methods in artificial intelligence. Finally, I would like to thank OpenMM Lab. Our study actually heavily relies on this great project. In fact, we directly used MM detection, MM segmentation, and MM action 2 for the development of Swin Transformer for object detection, sequential segmentation, and action regulation. So thanks OpenMM Lab, and thank you all for your attention. Thank you.
Goodbye, everyone.